Welcome back everyone. In the last lecture, we took two examples and showed you how to find out the controller gain or K values by which you can reach to the desired objectives. Today we take another example and try to go ahead from the point where we left. So here is another system which is of this form, and notice now this system has a 0 as well as 3 poles. The open loop transfer function has a 0 and 3 poles. Okay. And now the question is, determine the value of K so that we have a settling time of 3.2 seconds. It is a similar question like the previous one. So, the steps will be almost similar. However, the system has changed, the specification value has also changed. Okay. So, let us look at it again, how to solve this. Again the steps will be similar. Okay. So, again first let us find out the desired pole location. So, since Ts equal to 3.8, so zeta omega n will come out to be 1.25, and in this case the desired pole location will come out to be minus 1.25 plus minus j omega d. If you go ahead and draw the root locus for this system open loop transfer function, the root locus will look something like this. Here are your open loop poles, these are the two open loop poles, and this is your finite 0 which is as minus 3. So, in this case you see in the last case the branch was going to the left, in this case it will go to the right. There will be no root locus in the middle here, because to the right there are even number of points, even number of poles and zeros. So, this part will not have any root locus. So, the root locus will look something like this. So, where is the minus 1.25 line? So, the minus 1.25 line is somewhere here. So, this line cuts the root locus at this point, which means that I will be able to get to this closed loop pole locations with a value of K. So, now we will have to find out that value of K, but remember I am not yet sure what is the exact desired closed loop pole location, because I do not have the value of omega d, and in such a case we will go for the angle criteria, because you remember for magnitude criteria I will need the entire desired pole location. When I put it on the expression I get the value of K. Okay, but in this case since I do not have the desired pole location completely, first of all my second step rather should be now to find out the value of omega d. My first step was to find out the expression for the desired pole location. If it came out to be a clean expression where you do not have any variables, then well and good, directly magnitude criteria. First you check whether it lies on the root locus. If it lies on the root locus, then you can directly use the magnitude criteria. Okay. But if it does not lie on the root locus, then of course we will see what to do later. Okay. But now for the time being we know that this point at least minus 1.25 plus minus j omega d lies on the root locus, and I have to find out that point, and so we will go for angle criteria. So, what are the angles subtended at that point? You see tan inverse of, so from here these are the angles subtended, right. So, tan inverse of omega d, to form the 0 you will have a positive term. So, tan inverse of omega d, this is omega d, this expression is 3 minus 1.25. So, for the 0 you will have a positive contribution, and then from the poles you will have negative contributions, which will be again similar to the previous example. On the right hand side I am again taking minus pi, so that I can cancel this minus pi out. Okay. Finally, when you will solve it you will get that omega d will come out to be 1.714. Okay. Please see, I mean although I am writing this expression, I urge you again to solve this on your own and try to find out the solution. I might also make mistakes, who knows, right. So, better, why to trust me, better you solve it on your own and then check. Okay. So, omega d equal to 1.714 is what I got. So, my desired pole location, now we have a clean desired pole location, there are no unknowns in the desired pole location term. So, now I can directly go for the magnitude criteria, and the magnitude will come out to be say K equal to 5.2503. Now, at this magnitude, at this value of K, am I able to get to the desired pole location? Let us see that. So, here is my desired pole location. So, now let us see, go ahead and do the same thing like we did previously, write down the transfer function first. So, here is our transfer function, then you give the value of K, finally then write down the closed loop transfer function expression, which will be given by the function feedback. So, you use the feedback function and now we will find out the closed loop pole locations. So, now you look at the closed loop pole locations. So, the closed loop pole locations are at minus 1.25 plus minus 1.714, which is exactly what we desired. So, 2 of the closed loop pole locations are correctly placed. Where is the third one? The third one is at minus 3.5, and is this 5 times away from minus 1.25? No, right. So, you can expect trouble now. Okay, trouble is in you can expect that you have not met the criteria actually. Okay, because now, although see what is happening, we use second order systems formulas, but the system was not second order, right. In the previous example, in the last lecture's example, you had seen that the third pole by default came out to be 10 times away from the desired pole location, but in this case it is not. So, this pole will have influence on the system now. Okay. Not only that, look at the 0 location, there is a 0 as well. Okay. So, there is a 0 at minus 3. Now, if there is a 0 at minus 3, is the 0 5 times away from the closed loop pole locations? No, right. So, you see the 0, the 0 is also not 5 times away, the third pole is also not 10 times away from the desired pole locations. So, these two will have its effect on the response. Okay. So, what we desired, we will not get that, we desired 3.2 seconds. Okay. So, let us see the step response and see how much are we off, let us see that. So, if you find out the closed loop step response, so this is the response. Again you can go to the settling time and look at the settling time. The settling time is 2.74. This is not what we wanted. Why is this happening? Because you have a zero's influence, which is at minus 3, and then you have the third pole is also influencing because it is at minus 3 point something, right. So, this was not at all 10 times away from the dominant pole. So, we will have to recalibrate the value of k so that I can get to the exact point where I wanted to. Fine. So, what we will so this entire thing can be taken care of in a different way also. Like whatever we have done, we can follow these steps. Now, the next step would be that you change the value of k a bit and try to get to that point, okay, and see whether you are able to reach to that settling point, and then you keep on reiterating so that you can get to the value of k. I will take this problem again sometimes later so that I can show you what this reiteration process is like. But at this point of time, with an analytically when we are trying to find it out, we have reached a roadblock. The roadblock is that the value of k that we found out is not achieving what we desired. Now, if remember, if someone had given you a specification, say the settling time should be 3.2 seconds, it does not mean that you have to get to 3.2 seconds exactly. Okay. So, sometimes there may be some tolerance. If the tolerance is fine, so suppose the tolerance is that you can go from 2.5 to 3.5 seconds. Okay. And you tried to so then you try to design for design for 3.2 seconds, you ended up at 2.74, but this is okay because you had kept a big tolerance. So, whenever you try to design, you can always choose the tolerance value a bit higher. Okay. Suppose from the specifications that the user gave, the specific you found that it should have been 3.2 seconds the settling time, but you can always design it for 4.5 seconds, okay, and then see whether after designing, because of the effect of the poles, the third pole and the zeros, you can reach to that exact point. So, this is how you can reiterate as well. Okay. You can change the design parameters a bit and try to get to the exact point. Okay. So, what is happening here again? What is happening here? At k equal to 5.25, the desired pole locations had been achieved, but the problem is that you see at k equal to 5.25, the third pole also is moving, right. The third pole is moving to this. So, at k equal to 5.25, the third pole is somewhere around here, and that is why you are getting it to be minus 3.5. In the previous example, this 0 was not there. So, that the third pole was moving away from the imaginary axis or from the desired pole location. So, it turned out in that case it became more than 10 times from the desired pole location. So, in that case second order approximation was valid. On one more thing is visible from this, you see in this root locus you have no information about the 0 location. Okay, from the root locus you can only tell where are the closed loop pole locations, right, because root locus is nothing but the drawing of the closed loop poles, right, as k is varied, correct. So, but in this case you see, I mean the 0, there was a 0 here, right, the 0 was at -3, the 0 information is now nowhere captured. What is the closed loop 0 location? Okay. So, all these things matters and all these things becomes very important. That is why look at everything as a whole. In this case, for example, the third pole is not 10 times away from the two desired pole locations, and the 0 location is also very near to the desired pole locations. So, that is a problem. So, now another example. Okay, the last example we saw that we hit a roadblock, right. Here is another example. Suppose you are given this system, this is the exact system which we took in the previous lecture. Okay, first example. So, you have a system and suppose you have to find out the value of k which achieves 40% overshoots and 2 seconds settling time. Now, you have two specifications. In the previous cases you had only one specification. Okay, now you have to meet two specifications, 40% overshoots and 2 seconds settling time. So, now you have two formulas. So, MP 40% we know that zeta will be 0.28, and because settling time is given to be 2 seconds. So, we will have omega n to be 7.1429. Now, in this case you see you can directly find out what is the value of the desired pole location. So, the desired pole location will come out to be -2 plus minus j 6.8572. Now, if this desired pole location lies on the root locus, then you can find out a value of k. If this desired pole location does not lie on the root locus, you will not be able to find out a value of k. So, what is the root locus like? The root locus was like this, right. This is the exact, again this root locus we have seen earlier in earlier examples also. So, now the desired pole location is somewhere around here, you see, because it is -2 plus minus j 6.8572. So, -2 is this line. So, it is lying somewhere around here, right, where is this was our zeta line, right. So, at this zeta point, so it is -2. Okay. Now, you can see directly that the desired pole location does not lie on the root locus. So, if the desired pole location is not lying on the root locus, it is not possible to find out a value of k that will help you get to that point. You see the challenge, right. I mean, it is not that always you will be able to find out a value of k. In the previous example, for the same type of a system, we had only one specification. So, one specification you might be able to reach, okay. It is not guaranteed still, but you have to check whether that specification leads to an intersection on the root locus or not. That point there is a closed loop pole location which gives you that specification, then it is fine. But in general, in this case you see you have two specifications. So, meeting both the specifications became a challenge here. Okay. One specification which was only 40% was fine, but with this 2 second settling time also it becomes a challenge with just k. So, what can be an idea? So, an idea can be that, okay, is it somehow possible for me to change the root locus diagram itself? Okay, somehow if I can change the shape of the root locus such that the root locus passes through these points, then it is fine, right. Okay, that is the main idea, that is the main intuition that you should carry. How to do that we will talk about it in next lectures, but at least the intuition should be that since I know the desired pole location now, somehow the root locus should pass through that location. So, somehow I have to influence the root locus. In this setting I will not be able to influence the root locus. So, what should I do? We will have to think about that. Okay. So, let us take, so yeah, the desired location is not on the root locus. So, there exists no k for which we can achieve these specifications. So, see, the takeaway is that not all problems are solvable directly. Okay. You will have to go ahead and do something else also. So, if you have a problem, do not think that existing methods will always solve it. You might have to come up with your own idea, but in this case we know what to do, that I will tell you in the next lectures, but with a simple gain you cannot do this. Okay. So, let us look at another example. Now, let us take at that quadrotor example. Remember, we took in our mathematical modeling lectures, we took the quadrotor, we assumed that the quadrotor can move only in the z axis, okay, and then we found out the transfer function of the quadrotor, okay, based on acceleration as input and the position as the output, right. So, that was Zs. So, Zs was the output and acceleration was your input. Zs by As came out to be 1 by s square. We simplified the quadrotor. This quadrotor can only move along the z axis, and that led to a transfer function of this form. Now, the question that is being asked is that, okay, if this is the transfer function of the system, can we come out with a value of k such that I can reach to 40% overshoot. So, physically what is the meaning of this statement? You had a quadrotor and you want that the quadrotor should move to, so the reference here is unit step, right. So, u step. So, this is the reference signal here. So, since the reference signal u step, that means what you want is that the quadrotor should move up to 1 meter, say. Okay. So, the quadrotor has to move to 1 meter. Now, it says that 40% overshoot is allowed. What is the meaning of that? The quadrotor will move up, but then it can fluctuate about 1 meter up to 40%. So, that means it can go to 1.4 meters, come down, and then again it can settle, gradually it can settle to 1 meter. This is allowed. Okay. So, can I find out a value of k that will allow me to get to this response? Okay. So, now see, I have already translated this entire problem into a mathematical world. This is the problem that we have. So, now let us try to solve this using the ideas that we already know, because we have already solved 2-3 examples till now. So, let us see. So, the first step should be, you should find out the desired pole location. So, what is the desired pole location? The desired pole location will lead to zeta equal to 0.28. So, the desired pole location comes out to be this. This calculation we have already done, right, for 40%. So, zeta is 0.28. So, this will be the desired pole location. So, now we look at the root locus of 1 by s square. So, what is the root locus of 1 by s square? The root locus of 1 by s square will just lie on the imaginary axis, right. There are two poles here, and you try to find out, again use all the methods that we have talked about and try to find out the root locus. So, in this case the root locus will only lie on the imaginary axis. One branch will go down, one branch will go up, right, and the desired pole location is sitting somewhere around here, because this is minus 0.28 omega n. Okay. Now you see, you can directly see that this is not on the root locus. That means this is not possible. We won't be able to find out a solution with the help of k only. So, you cannot find out a k value by which you can get to this solution. This you could have seen in a different way also, because this is a very simple question. So, we can actually look at it in a different way also. So, how can we look at it? These are the steps we followed to design the controller gain, but I mean in a different perspective also you can look at it. What is the closed loop transfer function of this system? The closed loop transfer function of this system is k by s square by 1 plus k by s square, which comes out to be k by s square plus k, right. If this is the closed loop transfer function of the system, what are the poles of the closed loop system? So, that is the roots of the denominator. So, what are the roots of the denominator? S square plus k equal to 0, which is s equal to plus minus j root k. That means, the closed loop poles of the system are always on the imaginary axis. That is what you are seeing, right. You see the closed loop poles, the root locus is nothing but the collection of all the closed loop poles, right, as k is varied from 0 to infinity. You see all the closed loop poles lies on the imaginary axis. What is the meaning of that? If all the closed loop poles lies on the imaginary axis, that means the system will only keep on oscillating, right. It is an undamped system. Remember, if closed loop poles are on the imaginary axis, it is an undamped system. If it is on the complex part only, then it is an underdamped system. If it is on the real line, it becomes an overdamped system. Remember, we made that distinction. So, the idea is, see, during design everything comes together. Okay. So, I mean the root locus is also showing you that the system will only keep on oscillating. It is an undamped system. With a value of k, you can never get to the desired location. Okay. And that is what the root locus is also showing you. So, the desired location is not on the root locus. So, there exists no k for which we can achieve the specification. Further, since the closed loop poles are always on the imaginary axis, the system will always be undamped. The system will keep on oscillating. So, with a k, I cannot achieve my desire. So, if you only use a k and you think that your quadrotor will move to the 1 meter mark with some oscillations, no. What it will do is it will keep on oscillating only. It will not reach to that 1 meter mark. Okay. So, we have seen now that there are cases where only k will not be able to solve your problem. Okay. Somehow, again in this example, so somehow if I can manipulate the root locus so that it passes through that point, then I might be able to solve the problem. So, how do I manipulate the root locus? Somehow we will have to do that, right. So, basically we will have to replace this k by something else, okay, so that we are able to manipulate the root locus so that it passes through the desired location that we want. And that is what we are going to look in our next lecture. Thank you.